Hello everyone. So, we will get started with the third lecture. Recall that in the last lecture we were considering the following optimization problem, right. So, we consider a twice differentiable function whose domain is from Rn to R and a set S that is a subset of Rn, okay. And we want to find the minimum of f of x when x is restricted to S. Okay. So, this is the optimization problem that we are considering. Okay. And if you recall, we learnt two theorems in the last lecture. The first is let f be continuous function and S be closed and bounded. Then there exists a global solution for this problem, for the problem min f of x in where x is restricted to lie in the set S. Okay. So, this is the first theorem that we learnt, and that is regarding the existence of a global solution, and the second theorem is regarding the relationship between the local solution and a global solution. So, in case f is a convex function and S is a convex set, then x star is a local solution, implies x star is a global solution. Okay. So, yeah, these are the two theorems that we learnt. To give a recap of what is a convex function, okay. You can recall that f is convex if and only if f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y for all x y lambda in 0 1. So, for all x y and for all lambda in 0 1. Okay. The other condition is that there is, so if f is twice differentiable, then f is convex if and only if f double dash of x greater than or equal to 0 for all x. So, you just take the double derivative and verify whether it is non negative. So, this is when n is equal to 1. So, if I mean we consider any general n. So, this turns out to be as follows. You consider the Hessian matrix and verify whether this is positive definite for all x. Okay. So, this is possibly a simpler way when f is twice differentiable. So, again to recall, a convex set, right. So, S is a convex set if and only if x y in S implies lambda x plus 1 minus lambda into y also belongs to S for all lambda in 0 1. So, recalling the figures, a convex function looks like this. So, where if you draw a line between 2 points on the curve, the line always lies above the curve. So, this is a convex function, and when you have a function of this sort, where the line always lies below the curve, we call that a concave function. And when you have a function like this, so you have certain set of points where the line is below the curve and certain set of points where the line is above the curve. So, this function is neither convex nor concave. Okay. And regarding convex sets, you can recall that yeah. So, when you consider a set of this sort, where when you take any 2 points on the set and join it, you can see that all points in the line segment lie within the set. So, such a set is called as a convex set, and even when you have one pair of points for which this does not hold, such a set is not a convex set. Note that there is no concave set, a set is either convex or not convex. Okay. Right. So, with this, let us go to the next question. Okay. Note that we are actually looking at the problem min x in S min f of x subject to x in S, right. So, we have a few characterizations based on whether the solution that we are looking for is a global solution or a local solution, or whether a solution itself exists for a given problem. Okay. The more relevant question for this problem is, suppose a solution exists, how do we go about finding such a solution, right. So, we will start working on answering that question. Okay. So, recall that optimization problems are classified into unconstrained optimization problems and constrained optimization problems. So, it is unconstrained when S is equal to R n for some n, right. So, we start with an unconstrained optimization problem. So, consider the problem min f of x subject to x in R. Okay. So, we are actually considering an unconstrained problem where n is equal to 1. Okay. So, f is a function from the set of real values to maps the set of real values to a set of real values again. Okay. And we are having such an unconstrained optimization problem, and we want to find the local solution or global solution of a general problem, general unconstrained optimization problem. Okay. So, fine, the first step is to find the set of critical points. Okay. So, what is the set of critical points? we define the set of critical points. So, let me call that set C is the set of all x such that f dash of x is equal to 0. Okay. The first derivative of f vanishes. So, find all those points where f dash of x vanishes. So, we call that set a set of critical points, and yeah. So, if a solution is the local minimum or a local solution of the above problem, then it must be a critical point. Okay. So, so you must have learned this as the necessary conditions or the first order conditions, right. So, the necessary first order condition is that the local solution of the problem. Okay. So, yeah, this is a result. The local solution x star satisfies f dash of x star equal to 0. Okay. So, if a solution does not satisfy f dash of x equal to 0, then such a point cannot be a critical point. Okay. So, yeah, this is possibly something that is well known to you, but yes. So, note that this is only a necessary condition for a point to be the local solution. Okay. So, but it is not the sufficient condition. Okay. So, what is the sufficient condition? So, that is another result. A critical point is a local minimum if f double dash of x star. So, I will write critical point x star. Yeah, critical point x star is a local minimum if f double dash of x star is greater than 0. Okay. And it is a local minimum, sorry, a local maximum if f double dash of x star is less than 0. Okay. So, you can ask what happens if f double dash of x star is equal to 0. In such a case, further probe will be needed. So, we cannot say whether it is a local minimum or a local maximum or neither. Yeah. So, it can also turn out that f double dash of x star could be equal to 0, and such a critical point is neither the local minimum nor the local maximum. Okay. So, we will see a bunch of examples to understand what kind of point turns out to be the local minimum, what kind of points turns out to be the local maximum. Okay. So, let us consider f of x equal to x squared. Okay. So, in such a case, we first find the set of critical points, that is x such that 2x equal to 0, which is just the singleton 0. Okay. So, there is only one critical point 0, and what we know is that no other point can be a local solution, because it does not satisfy f dash of x equal to 0. So, there is only one point that satisfies f dash of x equal to 0, and that is x is equal to 0, right. Okay. And now when you look at whether this particular critical point is a local minimum or a local maximum or neither. So, you can see that f double dash of x equal to 2, which is greater than 0, right. So, this implies that x star equal to 0 is a local minimum of x squared. Okay. So, maybe I will write as f of x equal to x squared. Okay. So, okay. So, that is one example. Now, let us consider the example f of x equal to minus x squared. Okay. And here again the critical point is x such that minus 2 x equal to 0, which is again the singleton set 0. F double dash of x is minus 2, which is less than 0. Okay. Here you can see that x star equal to 0 is a local maximum of f of x equal to minus x squared. So, this result should not be surprising, because when you are maximizing a function you can consider minimizing the negative of the particular function, right. So, if you are maximizing minus x squared, then it is equivalent to minimizing x squared, right. So, that this result should not be surprising. Okay. But then we can have examples where so, let us consider f of x equal to x cube. Okay. Here you can see that the set of critical points is x such that 3x squared equal to 0, which is, so the critical point is 0 again, and f double dash of x is 6x, which is equal to 0 at, so you should write f double dash of x star is 6x star, which is equal to 0. If it is equal to 0, then from this result 2 that we have written above, right. So, we can not conclude whether it is a local minimum or a local maximum. Okay. So, in this case it turns out to be neither a local minimum or a local maximum. So, that you can actually find by I mean plotting x cube. I mean the example is simple enough. Okay. So, so if you plot x cube, you can see that it would look like this, and 0 is neither the local minimum or local maximum, and it is actually termed as saddle point. Okay. And so, if we again I mean, so it does not mean that if f double dash of x star is 0, it is neither a local minimum nor a local maximum. Okay. So, I mean you can see from the following examples. So, if you take f of x equal to x power 4, again the set of critical points is the same, it is just the singleton set 0, and f double dash of x star is 12 x star squared, which is 0. Okay. But if you plot f of x equal to x power 4, you will see that it is of this form, right. So, x is equal to 0 is actually a local minimum. Okay. In a similar way, if you consider f of x equal to minus x power 4, okay. So, you can see that this is again minus 4 x cube equal to 0, which is again only 0, and f double dash of x star is minus 12 x star squared, which is 0, but here 0 actually turns out to be a local maximum, which again can be observed from this plot minus x power 4. You can see that this point is a local maximum. Okay. So, what this tells us is that if you consider the problem min f of x subject to x in R. Okay. So, the first step is to find. So, I mean if you want to find the local solution solution of this problem, you first find the set of critical points which is x such that f dash of x equal to 0, and next step is for each critical point x star in C, determine find f double dash of x star. If f double dash of x star greater than 0, then x star is a local min. If f double dash of x star is less than 0, then x star is a local max, and if f double dash of x star is equal to 0, then further probe is needed. To determine whether x star is a local min, local max, or a saddle point. Okay. So, yeah, this is the case when n is equal to 1, that is when we are minimizing f of x when x belongs to R. So, this is actually a univariate function as we call it, because f depends only on one independent variable. But suppose if n is greater than 1, okay, that is when so I mean let us consider the setting when we are minimizing f of x1, x2 dot 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 xn, where each xi belongs to R. Okay. So, this is also an unconstrained optimization where the number of variables to be determined is n instead of just 1. Okay. So, we actually want to find the vector x1, x2 dot 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 xn, okay, instead of finding a scalar. So, how do you approach this problem? So, you can see that it will be just an extension of the procedure that I have given above. Okay. So, step 1 here is again find the set of critical points x such that the gradient of f is equal to 0. Okay. So, you can find the partial derivatives of f1, f2 dot dot dot, I mean dou f by dou x1, dou f by dou x2, dou f by dou x3 dot 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 dou f by dou xn. So, all n partial derivatives must be equal to 0. So, then yeah, such a point is called as a critical point. Okay. And for each critical point, now so note that x star is a vector, x1 star to xn star. In C, you need to find the Hessian matrix del 2 f of x star. Okay. So, that consists, I mean it is a matrix consisting of all the double derivatives, dou squared f by dou x1 squared, dou squared f by dou x1 dou x2 dot 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 dou squared f by dou x1 dou xn. So, this is something that we have seen in the last class, right. So, yeah, so for each critical point, so you find this matrix, okay, and how do we decide if I mean those are either local min, local max, or saddle point. So, you check the following value. Okay. So, take any vector t and find this quantity. Okay. If this is greater than 0 for all t in Rn cut 0, I mean, so other than 0. So, if you put 0, it is obviously going to be 0. but if you put anything other than 0, this quantity what we have written here must be positive. Okay. If that happens, then x star is a local min. Okay. And if this quantity is less than 0 for all non-negative n dimensional vectors, sorry non-zero n dimensional vectors, then x star is a local max. If there exists a T1 in Rn such that T1 transpose del 2 f of x star T1 is greater than 0, and there exists T2 in Rn such that T2 transpose del 2 f of x star T2 is less than 0, then x star is a saddle point. Okay. So, yeah, these are clear characterizations. When you have every T giving you T transpose Hessian into T positive, then x star is a local min. If every n dimensional vector T is giving you T transpose Hessian into T is less than 0, then x star is a local max. If you have one particular T giving you positive value and another particular T giving you negative value, then x star is a saddle point. Okay. So, we have not covered all cases, because we have not considered cases when T transpose del 2 f of x star T is equal to 0, right. If you even have one non-zero T where T transpose del 2 f of x star T is equal to 0, then further probe is needed. Okay. So, if there exists a T in Rn non-zero Rn such that T transpose del 2 f of x star T is equal to 0, then further probe is needed. Okay. So, yeah, you can see that the set of second order conditions is slightly more difficult than what you had for the univariate setting. Yeah, we will explain this a little further in the next lecture. Thank you.